Hello and welcome to Byte Sized. In this series, I give you a quick introduction to a math or computer science topic, teach you how to apply it, and tell you where to go if you want to learn more. Today, we're going to be covering Boolean algebra. Boolean algebra is at the core of everything you do when you're dealing with computers. If you're a developer, you come up against it all the time, anytime you deal with Booleans, or if you're writing if statements and you have like ands and ors in there. And even if you don't do any of that sort of stuff, every single computer you deal with is just a giant Boolean algebra machine because every integrated circuit is just composed of a bunch of logic gates, which are essentially just running Boolean algebra operations. So let's go ahead and jump right in. Before we jump into the methods of Boolean algebra, it's important that we understand what a Boolean is. So a Boolean can take on one of two values, those being true or false. A lot of the times, if you're seeing this in mathematical literature that's actually dealing with logic, then you're going to see this described as either a tautology or a contradiction. And you'll also see it represented by symbols like those seen here, or just being 1 and 0, as you see a lot in computer science. So now that we understand what a Boolean actually is, we can talk about what Boolean algebra is. So while in elementary algebra that you might have learned in school, you're dealing with numbers in some sort of number system, probably base 10, and doing operations like adding or subtracting or multiplying to them to be able to find a solution, in Boolean algebra you're doing the same thing, but you're doing it with logical operations like and or implies, which we will get into as we go along here. But you're doing the exact same things where you can use letters or other sorts of symbols to represent variables, and then you can solve logical expressions by using those same rules that you would in elementary algebra, but with the operators from Boolean algebra. So now, just before we get into the actual math, I want to introduce you to a core tool that we are going to use a lot, and that is called a truth table. So a truth table shows what the value of a given expression will be for the given values of certain variables. So here we have this expression right here. Don't worry about it if you don't understand what it says. And what we have here are three variables, p, q, and r. So in this truth table, you'll see right here that we have every single possible variation of those p, q, and r values, which I just did by counting up in binary here essentially. And then we have the values of this first part of the expression, which I labeled with 1 right here, and then the values of the entire expression right here. So this is going to be an extremely useful tool for visualizing what different logical operations mean, and also for solving things that we'll go over at the end of this video. So now let's get into the actual operators. The first operator is going to be not. So what not does is exactly what it sounds like. If you have a value of true, and then not true is going to be false. So if p was true and then you had not p would be false. So not is often represented by this symbol right here in Boolean algebra, but in computer science you will often see it represented by an exclamation point. Sometimes you'll also see it typed out as a tilde because this symbol's not on keyboards, and this right here is the logic gate representation. So if you're designing a circuit, this is what you would use for a not. Now, the next operator we're going to discuss is and. So and also does exactly what it sounds like. If you have an expression p and q, it will output true if both p and q are true, and false in every other case. So this is represented by this symbol, and again, it's two ampersands in computer science and can be thought of easily as multiplication if you think of the Boolean values as 1 and 0. I also want to take a second to talk about its inverse, which is called NAND. So NAND, as you see from the truth table right here, is the exact opposite of AND. It outputs true in every case except where both are true. This is really useful for circuit design because it can be implemented really easily electronically, and NAND has a unique property of being able to be used as a basis to then build any other logical operation that exists. The OR operation also does exactly what it sounds like. If you have P or Q, it will output true if either P or Q or both of them are true. It's represented by this symbol or two pipes in computer science. Now that we have those three basic operators out of the way, we can move on to the more advanced operators, starting with XOR. So XOR, it stands for exclusive OR, and it's essentially the same thing as OR, except for it outputs false in the case where both of them are true. If you take a look at how the truth table looks for P XOR Q, you will see that it essentially just outputs true whenever the two operands are not equals, which makes it so that oftentimes it is represented with a not equal sign. So the opposite of XOR also has its own symbol right here, and it is called a bijective or equals. And that does exactly what it sounds like as well, and outputs true if both of the operands are equal to one another. So now the final Boolean algebra operator, and probably the most complicated to explain, is implies. So what this does is essentially it checks whether you can make a material implication from the value of the first operand onto the second operand. So if you take a look at the truth table here, it will output true in every case except for where the first operand is true and the second operand is not true. You can read an implied statement like P implies Q as if P then Q, and then operate whether you can make that assumption for real. So if P is false, then we don't have enough information to make a material implication, which means that we cannot disprove it, so we output true. And then if P is true and Q is true, we also can't disprove that statement because the value of P and Q matches, which means that maybe P is able to make a material implication about Q. The only case where we can fully disprove this statement is the case where P is true and Q is not true, which is why that is the only case that evaluates to false. So with that, we have covered every single operand that exists in Boolean algebra. The other thing that exists is parentheses, which do the exact same things they do in normal algebra, which is just show precedence. So when you are dealing with Boolean algebra, the main thing that you're going to want to do is be able to simplify and manipulate statements. There are a lot of equivalences and laws that are really important to this, and in this video right now, I'm just going to go over the two that I think come up the most when you're doing this sort of simplification, but I have created a reference sheet, which I've linked in the description down below, that has every single equivalence and law that you may use when you're trying to simplify or modify expressions, so be sure to check that out if you're at all interested in doing any Boolean algebra, and you can use it to follow along with this video as well. So the thing that we're going to be dealing with first, and the most core law, is probably the most obvious, and that is the law of double negation. So the law of double negation states that the opposite of something's opposite is itself. So right here in this truth table, you can see we have the value of P, then we have the value of not P, which is just the opposite of the value of P, and then there we jump to the value of not P, which is going to just match the value of P, if you take a look right there. So that's the first law that is really important for doing this sort of simplification, and it comes up a lot. The next law we're going to go over is De Morgan's law, which is probably one of the best known Boolean algebra laws. And what it states is these two equivalences right here. So it states that not P and Q as one expression is the same as not P or not Q. If you notice there, what we did is we distributed that not to both of the operands there, and then we flipped the and into an or. And it also states the inverse for going from not P or Q into not P and not Q. So this can also be expanded to more complicated cases. For example, if you had not P and Q and R, then this can be applied and you have not P or not Q or not R. So De Morgan's law is really very useful for getting rid of parentheses and things like that, which can make things that you're doing in terms of simplification a lot easier and quicker, and is also important for a method that we're going to go over a little bit later to get to something called conjugative normal form. So as I mentioned before, there are also a bunch of other laws and equivalences that are important to know that I outlined in the handout that I linked down in the description. So I just outlined the two laws that I think are the most important for this sort of reduction and that come up all the time, but your main goal when you're doing any sort of reduction like this is probably to get your expression down to one of these two normal forms. So DNF stands for disjunctive normal form, and what it is it has the rule of being a bunch of and expressions that are combined by or expressions. And then CNF, on the other hand, is conjunctive normal form and is a bunch of or expressions which are combined by ands. So these two have the special features of both being in some sort of standard normal form, and also the guarantee that any single logical expression that exists will have equivalent expressions in DNF and CNF. Now, while the most intuitive strategy to get down to one of these forms would probably just to use those laws and equivalences that I outlined to do this algebraically, the other option is to use a little trick by using the truth tables that we outlined before. So just to recap, a truth table outlines our sort of input variables in our expression and then the value that we get at the end. So if you want to take something's truth table and find an equivalent DNF expression, you can simply go ahead and grab all of the rows where the answer ends up being true for the entire expression. So in that case, that's these four, and write those out as and expressions based on the values of the input variables. So for this first one to be true, we would need not P and not Q and not R. And then another option for this would be this second one right here, which would give us not P and Q and not R. And then another option would be, what's that, P and Q and not R. And then finally here we have P and Q and R. So this is a DNF form of this exact expression right up here by using its truth table. So you can also use this to get a CNF form. So to get a CNF form, what you're going to want to do is grab each of the columns in which the output is false. So as you see here, I outlined those all there. And using that, you can construct the DNF of the inverse of the equation. So right here, we have the DNF form of the opposite of this expression that we outlined right here, written out right here. So then to get this into the actual expression instead of the opposite of the expression, we can simply apply a not to the entire thing that we just built, our DNF right here. And then by applying De Morgan's law, we can switch that into, instead of being a bunch of or expressions, being a bunch of and expressions with inverses of these. And then if we apply De Morgan's law yet again, then we can get this down to be a bunch of or-based statements combined by and-based statements, which is our CNF form. And that is the truth table method for getting either DNF or CNF. With that, I've covered everything I wanted to for today, and you should have a pretty solid understanding of Boolean algebra. Boolean algebra is a very cool and very powerful field, but honestly, there is not that much to learn in it if you're just wanting to get started with the basics. So now, as a developer, you can probably transform a lot of your complicated logic. For example, you might have a bunch of nested if statements and things like that that interact, that you can condense down by using these laws of Boolean algebra into much more concise and to-the-point statements that have a lot more meaning than things might have before. And if you're trying to get into circuit design, this is obviously a core feature that you need. So now I just want to recommend a few resources. So the first one is an online course on Coursera called From NAND to Tetris. So this course goes way beyond the scope of just Boolean algebra, but its first couple sections did talk about circuit design and how you actually build up all of those logic gates from just using NAND as a starting tool. This is a really cool course for things like that, and then also for further things like learning assembly and just overall CPU design, which is a really cool option. So I highly recommend that. And then also I've linked a textbook down below from the same publishers that I like for a lot of other stuff on Boolean algebra. I haven't personally read this textbook, but that publisher is generally pretty good, so I think that that should give you a solid understanding as well. But overall, there's probably not much you need. If you just use my handout linked down in the description, you have all of the laws and equivalences that you need for Boolean algebra at your fingertips, and you should be able to solve or simplify pretty much any problem you look at. So I hope this gave you a better understanding. Be sure to like this video if you enjoyed it, and subscribe to me for more computer science and math content in the future, and I will see you in the next one. Goodbye.